Now let's take a look at speed and acceleration. When we were doing linear kinematics, we had v being used for linear speed. And the way we did that is we took a total distance divided by a time, or if we wanted to get the speed, we could also do the magnitude of delta x over t. If something was traveling in a circle, you'll remember from circular motion, we had a special formula where we would take the circumference of the circle, 2 pi r, and we would divide by the period. That was a distance traveled, one circumference, divided by the amount of time to travel that distance, and that gave us linear speed. When we look at rotational kinematics, now we're not looking at distance traveled. We're looking at how much angle is turned in a certain amount of time. So now what we're going to do is we're going to take that change in theta value, how much angle was turned, and divide by the amount of time that it takes to turn that much angle. And if you divide those two values, you're going to get what's called the angular speed. Now, just like we used v when we were talking about linear velocities, now we're going to be talking about a new variable, but in Greek, which is going to be omega. Funny looking W. All right, that's going to be your angular speed. It is important to keep in mind that this does not tell you how far something travels in terms of a distance. It's how much angle is turned per unit of time. If something is going to do one rotation, we would say a full rotation is going to be 2 pi radians, which we have right here. Then we say, okay, well, how long does it take to do one full rotation? Or how long does it take to do 2 pi radians? And that's going to be the period. And so to find angular speed, another way to do it is just take 2 pi radians, if you know how long that, you take 2 pi radians, and if you know how long one period is, you divide by the amount of time for one period. That will also give you angular speed. But that brings up a link between the linear kinematics that we did and the rotational kinematics. Remember, speed itself is not dependent on direction. So we can say that something moving in a circular path has some sort of speed. That's what we did with the formula for the circle, where we said v equals 2 pi r over period. But if we compare the formula for one rotation of something that is rotating, omega equals 2 pi over t, to our formula for something's speed when traveling in a circular path, 2 pi r over t, we see, oh, well, they share this highlighted section in common, which means if we want to figure out what the linear speed of an object is, or a point on something that is rotating, we can use the formula speed equals omega times r. Now, this is a formula that has been referenced on the AP test, and if you know this formula, it might help you get a question or two correct. But this is another formula that, for whatever reason, the College Board decided not to put it on your AP formula sheet. So there aren't a lot of formulas that we would say you should know going into the AP test, but this is kind of one that I would say that you should probably know before you take the AP test. So V equals omega R is kind of a useful extra formula to know when you're trying to connect linear motion to rotational motion. Now, the next thing that we want to look at is acceleration. When we did linear acceleration, we said that acceleration is not velocity divided by time. This is the important part. Good review here. Acceleration is the change in velocity over time. So we did v final minus v initial divided by the time, and that allowed us to get the linear acceleration. When we talk about something that is increasing the speed at which it rotates or decreasing the speed at which it rotates, now we're saying that that object has angular acceleration. And so to find the angular acceleration, the idea is going to be very similar in that there has to be a change in the angular speed. And then you're going to take the final angular speed minus the initial angular speed and divide by time. That's going to calculate your angular acceleration. Now, instead of an A, once again, we're using a Greek letter, alpha, to represent angular acceleration. So, kind of the key thing here is that rotation is going to be very similar to what we did with linear motion, except in a lot of cases, now what we're going to be using are Greek letters to represent these different quantities. So where we used x or y to represent linear position, now we're using theta to represent angular position. Where we used v to represent speed and velocity, now we're going to be using an omega to represent angular speed. Where we used a to represent linear acceleration, now we're going to be using alpha to represent angular acceleration.